Hey everybody, let's look at this one from 1981. It says we got a 10 kilogram block is being pushed along a rough horizontal surface by a constant force F as shown above. At time t equals 0, the velocity of the block is 6 meters per second in the same direction as the force. The coefficient of sliding friction, mu k, is 0.2. Assume g equals 10 meters per second per second. So first thing they ask is calculate the force necessary to keep the velocity constant there. So a constant velocity is to say that the acceleration is equal to 0. And if the acceleration is equal to 0, then the net force is equal to 0 as well. We've got this force F forward, but we got this friction backwards, and we know that those wind up being 0. So in other words, your force just has to be equal to the force of friction there. So all we have to do is calculate the force of friction. Force of friction is mu times normal force. In a nice case like this, where we're just sitting on a level surface with nothing pressing down or up, then the normal force will be equal to the weight. So we just wind up with mu is equal to mass times gravity. So let's just plug that in there. We got 0.2 for mu, mass is 10 kilograms, gravity is 10 meters per second squared, and we wind up with 20 newtons of friction force, and therefore 20 newtons that we have to push with to keep it moving at that constant speed there. All right, so next up, we are going to change the force. So it says the force is now changed to a larger constant value F prime. The block accelerates so that its kinetic energy increases by 60 joules while it slides a distance of 4 meters. Calculate the new force here. Well, what you should think of when they say that the energy increased by 60 joules is we change the kinetic energy by 60 joules. But whatever we change the kinetic energy by, that is equal to the net work done by us. So our net work was 60 joules. Also, we should realize that since the net work is 60 joules, we can say this: net work is equal to force times distance, technically times cosine of theta, but remember back in this picture, if we are pushing this way and it's moving this way, then the angle is 0 and cosine of 0 is 1. So we can just ignore that part when we push straight on. Let's plug in for these numbers right here. We know the net work, it was 60 joules. And so that is going to, oh, one thing I should say here too, when we find the net work, this is important. I should say it's the net force times the distance. And that's going to be important when we go to solve the final step here. So 60 joules is the net force times the distance of 4 meters, which means we can easily solve for the net force, which is going to be 15 newtons. That's not the force you push with. That's less than friction. That's the net force. So picture it like this. We've got this box, right? You are pushing with some applied force to the right. We know we've got some friction force back. It's 20 newtons to the left. This minus this has to be 15 newtons here. So in other words, the applied force minus the 20 newtons backwards has to be 15 newtons. So we can see from this that our new applied force, they call it F prime, has got to be equal to 35 newtons to cause it to gain 60 joules in 4 meters. All right, next part, part C. This part's pretty straightforward. It says calculate the acceleration of the block. Well, acceleration is simply Newton's second law, net force over mass. We have the net force, we just solved for it, it's 15 newtons. We have the mass, it's 10 kilograms. So it's simply 1.5 meters per second per second. All right, final part here. Okay, this part takes a bit more thought. And so it says once the block has reached a speed of 10 meters per second, the push ceases and the block slides to a stop. Why did it slide to a stop? Because friction is still acting on it. How far will it slide? So we're going to be looking for D there. All right, so now let's start to set this one up. So think about it like this. We know, according to the work energy theorem, that work is equal to the change in kinetic energy. We also know that work is force times distance times the cosine of the angle between the two, and that change in kinetic energy is the final kinetic energy minus the initial kinetic energy. But this final kinetic energy, if we come to a stop, is 0. So that one is gone there. Okay, so now let's start to expand this out. The force that is here is the force of friction. There's that distance that we're looking for, and the angle here is going to be 180 degrees. The reason for that is is now, as we stop pushing here, the block is going to continue to move this way, but friction is going to be back 180 degrees the other way. So the force of friction times distance times the cosine of the angle has got to be equal to minus the initial kinetic energy here. Well, we'll go and plug that in the next step. All right, so let's start to plug in. Well, here, I'll go ahead and do this. The initial kinetic energy is 1/2 times mass times initial velocity squared. Okay, so now let's start to plug in for some of these. We know the friction force. It is 20 newtons. We are looking for the distance. Cosine of 180 gives you a -1. That -1 is going to cancel out with this negative right here. And so we got 1/2 times the mass of 10 kilograms times the velocity initially of 10 meters per second. Don't forget to square that. So now that negative is gone. We got 20 newtons times the distance is equal to 10 squared is 100 times 10 is 1,000. Half of 1,000 is 500 here. 500 since this is an energy joules. And so last step we got to do here is simply divide to solve for the distance by 20 newtons. So 500 joules divided by 20 newtons winds up being 25 meters is the distance that we have slid.